Okay, we've started this problem, and here we go. Let's start back. Okay, so here's our second order rate law, integrated rate law, and what do we need to do then? We need, I told you to make up numbers, so what do you guys want to make up? Well, actually, I lied just a little bit. You got one number here. So if that is our, what is this?
Initial.
Okay, that's our initial concentration. What's our final concentration? How do I get it? 10% of that. Or you can say, since 90% has decomposed, you can say, so 0.020 molar times 0.9, that gives you 0.18. So that much is decomposed, leaving us with a very small amount, right? So you can take 10% of that. I'm just going to show you the longer process, just so you understand actually what's happening. So if you start with 0.020 and you minus, oh, it's actually, there's an O right there, okay? And you minus that much, that leaves you with how much? 0.02, yeah. So this is our final concentration left over. So that's going to be T final. So once you plug it in, let's go ahead and rearrange this and solve for T. Rearrange the variables before we plug it in. Go for it. Okay, so here's our final minus the initial. I like to just put boxes divided by K. K. Okay, so once you plug this information in, can you guys see that? I don't pull up because I need the books, but I need the information. Okay, so once you plug this information in, 1 over 0.0020 molar minus 1 over 0.02 molar. Make sure you're when you're typing this in calculator, watch your zeros. And then the K is 48 per molarity minute, because that's just liters per mole, which is just the inverse of molarity. Okay, what'd you get? Let me know. What'd you say, Tom? Oh, I thought you got it already. 9.4 minutes. The actual rate, what do you mean? And this is 2 sig figs. Yeah.
Why did the other mole for, oh, never mind. We get 1 side.
Well, yeah, we minus this and we divide it.
Yeah.
So. Okay, so those ones with percents, sometimes you got to kind of read between the lines and figure out how you're supposed to interpret that to get the information you need, because you can only have one unknown variable. All right, so 3's done. 4 is 0 order reaction. I'll wait a second because I'm still writing. Yeah. No, time is only in time. Is in time. Unit. That's the only unit there that's available. All right, the rate constant for a 0 order decomposition of high on a gold surface. Gold surface is serving as a what here? Catalyst, right? So gold is a great catalyst. It's an expensive catalyst, so it's not common. Platinum's a really common catalyst, actually. All right, on the surface is this. What is this representing? The K, the rate constant. How long, so question, time, how long will it take for the hydrogen iodine concentration to drop from this to this? So where's TI? Concentration, initial, sorry, I'm in thermochem and honors, I keep saying TI. Concentration initial, concentration final. Okay, integrated rate law, 0 order. You know this? Concentration final. Yeah, negative. First and 0 order are both negative. Second order is the only positive one. Got you. Okay, so plugging or solving for T. Go ahead and solve for T in terms of just variables. So final minus initial negative K. All right, so time is equal to final, which is 0.2 molar minus 1 molar divided by negative 0.050 molarity seconds. What's that time? Whenever we get there. Ready? 16 seconds. And you can see that molarity is going to cancel because you have molarity in the numerator here and then just simply in the numerator of the denominator here. So the molarities cancel. Seconds are on the bottom. You do that flippy flop, dot chop. I can't remember what you guys call it. Inverse it, you get time on top. I like to make up my own stuff. Flippy dot chop flop. Can I go forward? I got one more for you. Number 6. We did that one yesterday. Alright, decomposition of nitrogen dioxide is second order. I like it when they tell us what order it is. It takes 125 seconds for the concentration of NO2 to go from that to that. What's the K for this reaction? So first of all, what's the first thing I want to do? I want to do second order and then solve for K. Okay, so give me that second order.
1 over concentration N
Mm-hmm.
K.
I think Bryce could teach this. Okay, so give me K. Minus initial, right? T. I'm gonna erase that plus because it looks like a T and I want to see to say T right there. Okay. Okay, so plug it in, right? I'm gonna try to plug it here on the bottom. So 1 over, what's our final? 1 over 0.0104 molar minus 1 over 0.800 molar divided by time, 125 seconds. It kind of goes back between seconds and minutes too, so just watch your units because I want you to make you stop on your unit. Alright, so somebody tell me, make sure you put this in parentheses in the numerator if you're having issues with calculation. See here, we have 3 sig figs all the way, so I'm going to go 759 units per, look at the units. Molarity seconds. Molarity is still here. Yeah, we minused it. We didn't we didn't divide by molarity, so we didn't cancel molarity out. So K can have, funky units. And you know that K for second order is molarity seconds, because remember your rates, like if we wrote it like this, rate is equal to K times, whatever this was, squared. That's what a second order reaction is. How do you find K here? The units for it, I mean. This is molarity squared over here, there's something here, equals molarity per second. Well, there's molarity squared over here, there's molarity over here. That means we have to cancel one of the molarities, and that has to be done by K. Cool? Don't forget, you can always double check your units with the easier way, which I think is this way. Yeah.
Molarity be 5 seconds or wouldn't it be on top?
It's for, because right here, what I was showing you over here, this is molarity squared on top. One of these molarities over here have to get canceled to get rate to be molarity per second. Because rate's always, concentration change per second. So molarity has to be in the bottom of the K, which is what we've written here. Okay, what's the half-life of the reaction when the original concentration was this? What's the half-life equation for second order?
T 1 half equals 1 over K concentration.
Okay, and we have initial. Yeah, we have this, and we have K. So 1 over 0.759 per molarity seconds times the initial of 0.500 molarity. Alright, what's our T 1 half, or time of half-life? 2.64, yep. And you can see that molarity cancels here. Boom, boom, leaving with seconds. Seconds is the unit, has to be a time unit, so that makes sense. So you think you can feel a little bit better about doing 1 through 9 tonight? Yeah, okay, cool. Alright, mechanisms is pretty fun. You have what's it called, lecture notes for this too. It's before the mechanism worksheet where you see like a bunch of pictures someplace. Yes, did you take some pictures today? Find it. Because I just want to make sure we're all on the same page. But it's before that, so it's mechanism notes before that. Yep. Oh, this is on the website. I don't know if you looked at the notes on the website. This is a nice organized chart. If you take a picture right now, I don't care. There's also a little diagram in your notes that I printed for you that's got like every detail between rates, K units, integrated rate, half-life equations. This is everything you need to know. Yeah. Let me see. I'm gonna walk in front of this in a second. Okay, and I'm going to jet across. 3, 2, 1. Don't take a picture. Okay.
Oh. It's got like.
Let me get one for. See, there's one for Tommy. I don't know if you're gonna get lucky today, Tommy. We shall see. Do I see light? Nope, that's effort use. Oh yeah, I gotta give you guys more money for being good children.
Michael, you're the one who doesn't need it.
So yeah, Tommy, I'm sorry, you're out of luck right now. So, okay, I'll give you more money later. This is in your packet, BTEC notes. Okay, this is like one of the terminology part of the test. So if you don't know what an elementary step is, an intermediate, yada yada yada, and if I ask you to see multiple choice questions, you're gonna get wrong, which sucks. So write down what you need to here, and I'll explain in just a second. Okay, so I told you guys like we could draw reaction coordinates, and sometimes reactions occur in 1 step, 2 steps, 5 steps, 7 steps. Sometimes we care about the middle information, but most of the time we care about what's happening in the beginning and then what's occurring, what's being produced in the end. But there are steps called elementary steps. They're kind of easy to remember. They're going to be 1 elementary step, 2 elementary steps, but we can actually add up these elementary steps to show what the entire reaction looks like from beginning to end. So I'll show you how to do that in a second. Kind of, well, we'll cancel out reactants and products, but we're not going to put a delta H attached to it. Everybody likes this off, like a puzzle. Okay, intermediates, they can mean they are what they sound like. There's something that's produced in the middle of a reaction, but they're produced in the first step or an early step. So they're a product in an early step. And then they're consumed in a secondary elementary step, or a tertiary, a third elementary step. So they're occurring in the middle. They're not present in the very beginning or the very end. Okay, so they're going to be used up or consumed in a later step there. The RDS, rate determining step, is the most important thing that you need to know about mechanisms because it is the slowest step. It's the one that's going to hold up the reaction, hold up the rate of the reaction, and is the rate law. Like, it's what we've been talking about this whole time. I just haven't put a picture with the name yet. Getting ready to do that. Remember what molecularity means? Right there, just in case. Yeah, so the next definition. It's a BCE that tells us the coefficients that go with each of the reactants and products. So molecularity just tells us numbers for a BCE. And then catalyst. Does a catalyst get consumed in a reaction? No. So not consumed. Does it get used up in a reaction? No, it's the same thing as saying consumed. How else can I ask this? Yeah, I can't really ask it any other way. It's either, if I say it's consumed, you say no. If you say used up, there's no. So what happens is it's going to exist from beginning to end. You'll see it as a reactant and as a product, even though it's not actually being used up or being produced. It's just staying present in the whole solution wherever this thing's taking place. Or it could be like in a catalytic converter on the surface, or it can be on an electrode on a surface. It's just hanging out where the reaction is taking place. So these are just terms to know. Yeah. The rate determining step, because if I ask you what the rate determining step is and you've never actually seen that or heard that, you're like taking a wild guess, you know? So it's the slowest step, and most of the time on the AP exam, they'll write next to the reactant, the reaction, slow. And it like pretty much tells you the answer, but if you've never made that connection, then you're just like trying to, shoot in there, trying to figure out where to pull from. But you guys are gonna do fine on this. This is good stuff. But most of the vocab is pretty straightforward and actually makes sense with what we're talking about. All right, give me another second. You're still writing.
So what's a good catalyst?
What's a good catalyst? Good. You mean good like it can speed it up faster, or it's going to be staying with us longer?
How's it what about it makes it a catalyst?
That it will not react with a reactant to produce something else.
So why does it bring the other? That's what I'm thinking.
Well, if we're talking about enzymes, then it's got specific active sites that fit perfectly with substrates. If we're talking about surfaces, I'll show you some pictures that might help with it. Let me think about that because that's not an easy question. Okay, I'm gonna go past this because this is just vocab. You can look this up in your book. Okay, so for reactions that we've been doing the rates of reactions, I'm now going to tell you the baby steps that go with the entire BCE that we've been talking about. So I've been writing these reactions up there, but there's stuff in the middle where that yield mark is. There's multiple steps there. Now we're going to talk about those multiple steps. Okay, so I'm going to tell you about mechanisms, and there are 2 criteria that must be met for something to be a good mechanism for whatever BCE I give you. The 2 criteria are the sum of all elementary steps has to equal the overall, which is just the BC that I've been giving you, the overall BC. So this is that when you're summing up or adding elementary steps, this is kind of like Hess's law. And that in quotation marks is not really Hess's law, but it's just a version of it where you can cancel products and reactants to make your overall BC. So that's the first criteria. The second criteria, rate law. The rate law that is written for that specific reaction will match the slow step. It'll match the rate determining step. So let me write that K in. It's awful. If I told you the rate for some reaction was rate equals K, A to the first, B to the first, what would the rate determining step look like? What would the reactants be? If I told you the rate was K, rate equals K times A to the first, B to the first, what would the rate determining steps reactants be? A plus B. Because this rate law is matching the slow step, because the slow step is holding us up. It's holding up the rate, so it's going to be determining the rate. That's why it's called the rate determining step. It determines the rate law. So the rate, whatever this is, it'd be A plus B yields blah blah blah. I don't really care what the products are because rate has nothing to do with products. Rate only, you're only concerned with the reactants here. So I like to say you're as slow as your weakest link because, I mean, if you've got a slow step, that's holding up the process. So the entire rate is determined by the slowest step, which is the rate determining step. And you can't be slower than your rate determining step. That's the thing that's kind of controlling the kinetics. Lastly, we have these things called bimolecular, tri or termolecular. You guys want to hear chemistry? So sometimes we talk about how many collisions, like what kind of things or how many reactants are colliding together. Realistically, we can't. It's hard to get like 3 things coming at the same orientation, at the correct orientation with the correct activation energy to collide. Remember the whole collision theory, you gotta have enough energy, they're collide in their correct orientation. It's hard to get 3 things doing that, but it's easy to get 2 things doing that. So most of the time we'll see bimolecular steps where you have two things colliding. Unimolecular, there's not really anything colliding with one another. Most of the time it's just going to be decomposing by energy, so it's going to be breaking apart. Sometimes you'll have catalysts for that one too. Termolecular is really rare to see because it's hard to get 3 things in the same place. Okay? Yeah. What determines the speed? Lots of stuff. Lots of stuff. So the rate is going to be the speed of the reaction. That rate determining step determines the rate, and it's going to depend on temperature, the type of reactants, the surface area, the rest of the environment? Are there competing catalysts? Are there competing substrates? Stuff like that.
That's already given.
Yeah. Okay, so here's your first one. First thing I want you to do, so what's happening here is I'm showing you the 2 elementary steps for this overall BCE. So what was the first criteria for a mechanism to be a possibility for that entire reaction? Right, so these elementary steps here must add up to equal this up here. Let's double check. Okay, so do you see this on this side?
Yeah.
Yes, so this and this can cancel out, right? Okay, do you see this anywhere else? No? This?
Yes.
Yes. Anything else? No, okay, so what's the BCE? So just bring it down, right? NO2. Does this match the reaction given? Yes, okay. So the reason we have to say is it's a viable mechanism is because, yeah, we know that the starting point is this and the ending point is this. We can figure out what the reactants are, what the products are, but not it's really hard to figure out what's happening in the middle. So we propose mechanisms that would meet this BCE, but we don't really know if this is true because we can't isolate intermediates. We can isolate catalysts. So these are just theories as to how something occurs. All right, so I canceled out some stuff, and you canceled out some stuff. Which ones are the intermediates that we canceled? There's only one intermediate here. NO3, definition of intermediate. It's not present. Formed in the first reaction and then consumed in the second reaction, right? That's the definition of intermediate. So this is the intermediate. Okay, 2 is the catalyst. Okay, it has to be present from beginning to end, right? The NO2. Okay, so a catalyst is not actually a reactant. It's just there. See how NO2 was just there? And it was just there? It was present from beginning to end, but it's not actually listed. Actually, it is listed, but there's just another reactant there. That's the reactant product. Okay, so it's present from beginning to end. That's our catalyst. Can we answer all those questions? Yeah, we did. Okay, and then which step is the rate determining step? Why the first one? Okay, so this is the rate, right? The rate will be, the molecularity will match the slowest step. It'll match one of these elementary steps. So we see that NO2 is squared. What does that actually mean about the molecularity? It means there's 2 of them. So you have 2 NO2s yielding to products. So which of these match that? The first one. So this is the rate determining step right here. Because we see that we have 2 NO2s right here.
So that indicates second order.
It does indicate second order. This whole reaction overall is second order. But if I want you to identify the RDS, you have to look for the one that the molecularity matches. Like this is going to tell us that there's 2 NO2s reacting.
So if we had this and we were writing it, can we just write 2? We know it's second order because there's 2.
No. Because second order, okay, determine order, you need experimental data, right? But that's for us to determine this rate law. We are given the rate law here, and we know that the rate law is determined by an elementary step. One of the steps that's the slowest. I'm giving you the steps, and the rule is the rate law is determined by the molecularity, which is the BCE, of the slowest step. So this is actually coming from the BCE. And normally I tell you can't do that because I usually give you data for rate laws. In this case, I'm giving you the baby steps of the rate. So you can actually say, yes, this 2 comes from the coefficient in the rate determining step. Okay, usually you can't do that. It's only when you have elementary steps you can do that. Yeah.
How do you know that one is the slowest?
Because it's the only one that matches the rate determining the rate. The rate says it's NO2 squared, which there's 2 NO2s. That's the only one with that as a reactant.
Wait, did it give you? Oh, yes.
Yes, I have to give you that data information. I would like to go forward. Okay, so I'd like for you to draw this. This was the one that was similar to the one that was on the AP exam last year, and most people got tripped up because it's very, very rare to actually see a 2-step reaction because most of the time they just write the big reaction curve and that's it. This time they tell you it's at 2 elementary steps. Here are the 2 steps. Here's the activation for each step. draw this, sketch this, and write down these information pieces, because this is something that I see them asking you to interpret diagrams, something like this. I'm trying to predict, and I have a confidant that kind of helps me with my predictions, because I'm totally not into looking at an old test and trying to figure out when they ask the same question again. So you'll see, we know that these are potential energy diagrams. You'll see the first step has a high EA, high activation energy, which means that that reaction has put forth a lot of energy to get to that transition state. That transition state is kind of that not isolate, you can't isolate that. We're assuming that's what it looks like, something like that, but we don't know for sure. It's just a theory on how this mechanism occurs. So that first elementary step forms some products. Those products are going to then react again in a secondary elementary step, or a second elementary step. But this one's way easier, because look at that little activation energy. It's like nothing. Okay, they can easily overcome that second activation energy. And then, so these are kind of like the first products, and then here's the second products down here. So these products serve as a reactant again for the second elementary step. I'll scroll up in just a second, Tommy. I'm just going to let people get that top one. I just want to let you, I'll scroll down so you can see the bottom. So this is really important, because this graph is telling you is that the first elementary step is the rate determining step, because it's going to be the slowest. Why is it the slowest? Yeah, this activation energy is going to be hard to overcome, so it's going to take a while to get all the way up here. So the ones with the highest activation energy tend to be the slowest, because it's going to take a while to build up and have enough energy, or it's going to take a while for enough collisions to occur with the correct energy for the reaction to actually occur. It's more about the collision. So that's why this important, that little piece up there is really important. And then once that happens, the first elementary step is done, the slow step is done, the second reaction is very fast. That second elementary step is very fast, because the activation energy is very low. Yeah. They would probably ask which is the rate determining step, but they would not label anything, like really anything. Now this would be a small part of a large question. Yeah, this would be like maybe a kinetics or a thermochem question, because you see the delta H's on there too. They could ask a lot about thermodynamics too. They might even get into Gibbs. So they would have to give you a reaction. This would be a small part of it for the FRQ question, and then they could ask about what's the Gibbs free energy, is it spontaneous, thermodynamically favored, stuff like that. And then if you want to see, they've labeled here step 1 to that first drop-off point, and then step 2 to the second drop-off point. Cool? Scroll up. So I probably put a picture or some sort of diagram on your test too. So this is something cool to go back and look at. And I'll pull in a little bit of delta H. Obviously, what kind of reaction is this, Endo or exo? Overall reaction. It's overall exo, right? So this would feel hot to the touch. Be probably thermodynamically favored, because most of the time exo is, but it also depends on the what? The what? Well, Gibbs free energy is a combination of both enthalpy and entropy. Thank you. Yeah. If you want, the first part was more important. Okay, I'm going to go forward because we got a couple more to do here. Okay, so for this example, you got your BCE, you got your rate law, gives you everything you need. A suggested mechanism, so someone has suggested this mechanism will work. Let's see if it's possible. What do I do first? What are the two criteria that have to meet? We sum, okay. Sum it first. Tell me what I cancel. Huh? F, so NO2 is present here but not over here, so I can't cancel that one. F is present here and here. When F is just written like that, it's actually a free radical. Free radicals actually are usually written as F with a little dot next to it because it's got an extra electron. Free radicals are very, 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 very reactive. You know the antioxidants you eat, like blueberries, raspberries, stuff with antioxidants in it? Antioxidants oxidize the free radicals in your body. Free radicals damage your organs and can cause you to, die an early death. There's lots of issues. So if you breathe in free radicals, which we do on a daily basis, just from the air, it can damage your tissues and organs. But if you eat things with antioxidants, it corrects that. So eat your blueberries and other stuff. Okay, so that's what a free radical looks like. That's off topic. What else is present? Anything else? That's it, right? Okay, so NO2 stays. F2 stays. This NO2 stays. So I'm just going to put 2 out front. Okay, yields this thing. 2. Okay, does this match this? True. Yes, cool. So first criteria is met. BCE is the same. Okay, what's the second criteria we have to meet?
A rate law written from the coefficients of the rate determining state must match the experimental rate law.
Okay, so the rate law written from the rate determining step reactants from the coefficients has to match. So here's the reactants of the slow step. It says slow, but we know that means rate determining. Does that match that? Yes, because this is a 1 here, 1 here, 1 here, 1 here, matches. So is this possible? Definitely, yeah. Excuse me?
That's 2 on the 2.
What? I'm only looking at, for the rate law, I'm only looking at the slow step, because the slow step determines how fast I can go, which determines the rate.
Oh, so we're just picking out this one.
We're picking out the slow step and looking at how it matches. Yep. Anything else I want to tell you here? No, let's go forward. Okay. Label the catalyst and intermediates. Intermediates first. Sorry, give me intermediates first.
And
NO2 is an intermediate. It has to be produced in the first reaction and consumed in the second. Okay, so here's our intermediate. Where's our catalyst? So intermediates are just, they're transient. They're formed and then consumed immediately.
well, what about NO?
We're starting with NO and we're ending with NO. So that's the catalyst. It's never consumed. It stays with us from beginning to end because catalysts are not consumed. Catalysts help the reaction along and they stay present the entire time. But intermediate,
NO2 and intermediate.
because it's not here to begin with, we form it.
It's not in the first reaction.
It's not in the reactants of the first reaction. It's formed really quickly and then consumed very quickly, and it's not present in the end. Maybe. It depends on how stable your intermediate is. Some intermediates are very unstable, and they're really, really reactive, and they react really fast, and you never see the intermediate. Unless you can slow down the reaction. Really slow. But then you're doing kinetics, you want it to occur fast. Yeah, you get one of those that go that slow. Okay, so what's the overall reaction? What cancels when I'm asking? Hold on, NO cancels, NO2 cancels, leaving us with
3 first.
guess what reaction that is?
Nothing. There's
That is a reaction. Where do you think that occurs? That's the ozone. This is ozone reacting with free radicals of oxygen to form the gas we need to breathe. This is how we make the oxygen gas in the air. Okay, this is also reversible. So this could occur this way, where 2 oxygen molecules react to form ozone, which we need to happen because our ozone layer is slowly degrading. There's a lot of environmental chemistry in here. I wish I could teach apes. So, proposed mechanism for this one is this. Write the overall rate law expected. Right now, automatically, we can write the rate law. Go for it. Who determines? Hear you.
4H9BR.
1. How do we know that?
That's in the reactants of the slow.
Okay, so we know the rate law is concurrent with the rate determining step. The rate determining step is the slow step. When it says slow, it's the slow RDS. So all we do is we choose the reactants present, we put it in a rate law, and we're done. Yeah.
So the coefficient, if there was a coefficient, so if we had a 2 coefficient, it'd be
To the second.
to the second.
Mm-hmm.
What does RDS stand for?
Rate determining step. It's the rate determining step. Elementary step. Cool. Okay. Blah, blah, blah. What's the overall balance equation for this reaction? Give it to me. What do I cancel? What's the first
The
thing?
OH thingies.
C4H9.
Okay, plus the cation can cancel here, and then the what?
The C4H9OH.
That thing. Anything else? Nope. That's it. Okay, so pull everything down. What's present? Hold on, I gotta get this first, right? C4H9Br plus 2H2O yields Br minus and that thing. You know, what's the name of that?
Butane.
Ethanol.
Butanol. Butanol. Good job. Those are smart cookies. Okay. So there's our overall reaction. What are the intermediates? Who are the intermediates? So here's an intermediate because it's formed and then consumed. This one's formed and then consumed. Good job. Awesomeness.
It's about to get harder.
No. Well, okay. Yeah, I do have one. I have one that's kind of out there. You know that always happens. Huh? No. Yeah. Was there a catalyst in the last one? Nada. Because I would have had to cancel here and then here.
Oh,
And I didn't cancel anything from the reactant you brought it. Alright, the mechanism for nitrogen dioxide, blah, 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 blah. That. Write the rate law. Rate law. Bless you. That was awesome. Okay, rate law. Okay, what?
Concentration.
Squared. Thank you. I was waiting for that squared. Because there's 2 here, so I can just call that squared. Okay, what is the overall balance equation? We don't need to do this anymore, right? Can I go to the next one? Yeah.
Why is it squared if it has a catalyst?
Because technically, the
Here,
slow
let's think
step.
about Rubens.
Hold on. Let me verify that where it's at. Because technically, the slow step, as written, the molecularity has to match. Molecularity has to match. Okay. Okay. This is the hard one. Thank you, Bryce. Okay, I didn't finish that. You guys can finish that. Okay, so for this mechanism, for this reaction written above, here we have the reaction. 2 scientists have proposed 2 different mechanisms because you can propose whatever you want as long as it meets those 2 criteria. So we have this first one and then the second one proposed. Do both of them meet the criteria? Does only one meet the criteria? Which is the best match for the reaction given? All right, so first criteria you want to check is what? The sum. Okay, let's check this one first. Sum it up. What can I cancel?
H2O.
N2O.
That's it.
Okay, cool. Write it out.
2NO plus 2H2O.
That and that, right? Does that match?
Beautiful.
Okay, slow step. What's the rate for this one though? Tell me what it says.
K concentration and
Concentration.
All right, and that matches, right? All right, so that's in the running for it. Let's check the second one. All right, so so this is the 2-step mechanism. 2-step mechanisms are very common because it's easy enough to form an intermediate, react the intermediate, and you're done. Like that little thing you drew, that's a 2-step mechanism. All right, so this one's a 3-step mechanism. A little bit more coordination going on here.
Wait, Miss Emma, why would you check that one for rate?
Because I want you to tell me about, if I asked you why, you'd have to explain why, so you have to have a comparison.
You can't just say the rate law because the RDS.
Just wait. All right, so first of all, let's sum this up. What cancels?
N2O2. Is
And
that a catalyst?
that's intermediate here.
Why?
N2O2.
That's a catalyst.
No, it has to. If it's formed and then consumed, it's intermediate. This one's formed and then consumed, it's intermediate. Anything else?
Just being reversible.
Yes, being reversible means something. That's what I'm going to get to in just a second. Okay, so 2NO plus 2H2 yields N2 plus 2H2O. So it does match the molecularity of the entire reaction, so it's still in the running. Okay, so this reversible reaction is called fast equilibrium. Fast equilibrium. Because it's reversible, as soon as these 2 NOs come into contact, they form N2O2. Or, if this was present, it could form 2 NOs. It's very, very quick. It happens as, half a nanosecond or something like that. So, what do you notice about, we want 2 NOs in the slow step, right? Because that would match the rate law. Technically, this right here, that's in that flow step, what actually can this also represent? 2 NOs, because it's a fast equilibrium, which is a reversible reaction. So technically, this slow step does match the rate term, or the rate, because since these two things are essentially equivalent, we can substitute into this right here, because it occurs in a fast equilibrium so quickly. Does that make sense? Yeah. So you would say, due to the fast equilibrium step occurring, the rate determining step does match the rate law proposed, or the rate law of that reaction. So both of them are viable options for the suggested mechanism. But you might say a 2-step mechanism would occur easier than a 3-step mechanism, and that might be why you choose the top one. But if you explained it, you would probably get credit if you also chose this one to say the equilibrium, this fast equilibrium occurs, without hesitation, without activation energy, whatever. Yeah.
Why is it slow?
If this one was slow,
Yeah.
it wouldn't say that, because then you wouldn't know who would be your reactant at that point. So I just said a lot. I hope you wrote that down. Yeah.
So because the first, then that means that the N2 switched out for something.
Let me show you a little bit more detail then. I was hoping someone would ask me, because I really wanted to do this part. I didn't want to do it if no one asked me. Okay. So if this was let me do it this way. The rate of the fast equilibrium step. Okay, so in accordance with this equation, we can say rate equals NO squared, right? If this was going to be the thing we're talking about, we're just trying to get the rate out there. But it also equals this one, because it's a reversible reaction, it actually can be consumed as a reactant. It also equals this. I'm gonna write this. Yeah, I'll write this like this, so I can see what's happening. All right, so these two things are equal because their rates are equal because it's in equilibrium. One occurs the opposite, it's still fine. The rates are equal. If I rearrange this and solve for into O2 concentration, I'm gonna call this K1 and K2 since the K's here, one's for that first reactant, one's for the product here. You can divide by K2, divide by K2, leaving this by itself, where you have N2O2, yields K1 over K2 times the concentration of N2O squared. Okay, so this right here is just this K here, these two K's on top of one another, we can condense that into a smaller constant. So into O2 equals K3. I'm just going to keep adding my K's here. So since these two things are equal, whenever you're looking at, when you're looking at this top thing right here, the rate that you want it to be, and you see that you already have this present in the slow step of this actual proposed mechanism. This N2O2 that you want to put in the rate law equals this over here, which is what's in the proposed mechanism. I don't know if that makes any sense. But essentially, this one would say rate equals into K into O2 times H2, because that's a slow step, and that would be the rate written as is from this specific example. But since this equals this, you can substitute this in right here. So when you substitute that in right there, you get rate equals to K, that thing, K3 NO squared H2. But these two K's can come together as one K, and that matches the rate. That was a big long explanation to say that these two things are equivalent. Okay, so it does work. If you went through the mechanism, changing around the K's, because K is just a constant, you don't really care what K is right here. It's a constant. It equals the rate proposed. So both of them are viable options. All right, that's just to help you see the molecularity I don't think you need to write any of this down. This should just help you see it. One product, molecularity of one, two. I mean, sorry, one reactant, two reactants, two reactants, two, three reactants, three. Okay, so just call them molecularity. That's what I've been saying. And then the rate law those are the rate determining steps, and the rate laws would be written as is. Cool with that? Huh?
Is that third order? Fourth one?
This would be third order overall. This would be third overall. This would be third overall. Yeah, that's why these are very rare. It's hard to get three things to react, to correct radiation and activation energy at the same time. You've already seen that. You don't need to see that again. This is just I just had a bunch of pictures. This is that intermediate thing that we think that's what it looks like, but we can't isolate it very well, so it's hard to actually say that that's an intermediate. These are just cool pictures I found. Sometimes a catalyst can be present. So this is that oxygen one, the ozone, and then the oxygen form. This would be how much energy it takes to be if it was uncatalyzed, and this would be how much energy, so activation energy, it requires if it was catalyzed. This is going to be a two mechanism step, which we saw in that 2 examples ago with the ozone. So it was a 2 elementary step, which is why you see these cute little humps right here. That requires a catalyst. A lot of times there's other radicals in the air that are catalysts. Okay, I think I'm going to be done. I don't know if I have anything else for you. Do I want to do this right now? I might do that in a minute. Go ahead and start the mechanisms practice worksheet. I might do one more thing with you because there's 2 more slides on bond dissociation energies that I have to put together. So, start the mechanism practice worksheet. I have one person that's going to present for this unit. Number 12. I think it was for Ann. Who was it? Lydia. So start number 12 first because I want to have you do that right now. I'm going to pause this video for a minute. Stop. Oh, no.